Hello and welcome to EP2P04. This is going to be a practice problem for topic number 3, moments and 3D static equilibrium. Okay, so this one is practice problem number 2, Nouveau, Beamo, Slideau, and we're going to consider this totally new structure, which is definitely not a slight change on the previous one I was showing in 3D, and it's made of rigid beams. So these are all rigid things. They can't bend. There's no flexibility in them, no elasticity. Point A is a fixed support to the ground, and it's also the origin. Point B refers to the slider joint, which is the location of the frictionless orange pin. So this is a vertical slider that can go up and down. So it can't provide any force in the y direction. We'll see this is the y direction at 0, 0.5, and 0. And point D, it tells you later, is 0.05, slightly more to the right, 1.3, and 0 and z. So this is the y direction going up, x is to the right, and z must be out of the page a little bit. So yeah, point B is the slider joint located there. This cannot provide a force in y, but it can provide forces in x or z to resist motion. So it will not allow this beam to move to the right. It won't allow it to move out of the page. And it won't allow any rotations. So this doesn't allow it to bend down, doesn't allow it to rotate about y, like in and out of the page rotation, and it doesn't allow it to rotate about x, which would be like a twisting of this beam. Right. So that's what the slider joint does. In addition, we have a cable DC which connects point C to point D up there, and we're given the coordinates, and they're not quite the same coordinates as in the similar looking problem in the notes. 3 external forces are applied to the gray beam, F1, F2, and F3, and these are given the following values: 2, 3, and negative 0.4 for F2, so that's 2 over, 3 up, negative 0.4 slightly back. F1 is 0.2 to the right, negative 0.4 up, so in other words 0.4 down, and mostly in positive z, 4 out. And we have the coordinates of these as well. F3 components also given there. So what we're asked is this system as a whole externally statically determinate, underdeterminate, or indeterminate? What about the system of the gray beam alone? So the whole thing, is it externally statically determinate, underdeterminate, or indeterminate? So the whole thing has this fixed support at the bottom, and anything else like the cable and the support here is an internal thing. So with a fixed support, and exactly one fixed support, we can deal with any externally applied forces, and we'll be able to solve for the 3 force reactions and 3 moment reactions uniquely. So this is statically determinate as an entire system. For the gray beam by itself, we have 5 possible reactions with 1 degree of freedom there, and one unknown reaction, 1 unknown force we could provide in this direction, with 5 degrees of freedom over here for the cable connection, 5.5 if it was trying to move up. So to check whether with the cable it's a little bit tricky, right? Because it might be that we are statically underdeterminate with the cable if force 3 is not strong enough to overpower force 2. This is the main down thing. Force 1 doesn't have much up or down. So let's just compare force 3 and force 2's vertical component. So force 3 is -5 in y, and force 2 is +3 in y. So it looks like we do have enough downward force on this bar that the cable is indeed going to need to be in tension. And that's good, because that's the only place we can get upward force to stop this from being pulled down, since this joint can't give us any upward force. So once that's the case, the cable in pulling up, it can't just pull up, it has to pull up and mostly to the left, and this joint can oppose that leftward motion and can also oppose any of the other things that are going on from the forces. So looks like we have the right kind of supports as well. We have the right number of variables. We're going to have 5 from this and 1 from this. That's 6 unknowns, and they don't they're not lining up in the wrong way so that we can't actually support the structure. So it looks like we are statically determinate for the gray bar as well. If this is kind of complicated, if you have trouble seeing that analysis and verifying that we do have the right ones, the right variables, then you'll also, the good news is you can just start the problem And if it turns out it wasn't statically determinate, then you'll have some issue. If it was indeterminate, you will just have parameters at the end. You won't be able to solve for them. If it was underdeterminate, you will have unsatisfied equations, meaning there's no solution. Next, we're going to try and find out the reaction forces and moments at A, or state why it's impossible. So it isn't impossible. It should be able to work. So let's see if we can get that to work. Okay. So as before, we'll restart and include the linear algebra package, and then we will say we'll input the variables we're going to need. So to figure out what the reaction forces at A are, we actually don't need these locations of internal points. We'll need those later, but we will need what the forces are and where they are applied. Yeah, so let's explain why. So maybe do some algebra over here first. So what we're going to use is we're going to say that the net force on, or maybe the sum of the forces on ABC, that is, or rather ABD is this beam. Actually, wait. Hold on, scratch that. Sum of the forces on the whole system for the system as a whole. I've got the equation. You can't see it, but the equation is right there. Okay. Yeah, there we go. For the system as a whole, we've got that the net force is equal to 0. And the net force would be equal to the reaction force acting at A plus F1 plus hit the caps lock there, F2 plus F3. Okay. And the net torque is also equal to 0. So the sum of the torques about any point, get our vector symbol there, because there's no way to make this bold easily in math type, so it's actually easier to just add the vector symbol on top. Okay, so the net torque about the origin, let's say, that's going to be the easiest point, but we could pick any point we like, is also equal to 0. And this is going to be the reaction moment at A plus 0 cross FA. Conveniently, that is the origin, so we can cancel out its torque. If it wasn't at the origin, if the support was somewhere else, then we would have to put in a non-zero moment arm there. Right. So 0 cross FA plus F1. Well, it's moment arm, so that's R1 cross F1 plus R2 cross F2 plus R3 cross F3. And I think we have the space to make the equation a little bit larger. There we go. Yeah. So that tells us what the moment is, because we know all of those other things in there. So despite the fact that these are vector equations, we can totally solve them, no problem, here in Maple. And that'll be first putting these things in. F1, 0.2, negative 0.44, and R1 is 1.1, 0.48, and 0.02. Be really careful, double check, look back after you do each of these, because this is a very easy spot to mess up the problem. 2, 3, and negative 0.4, and R2 is 0.4, 0.55, and negative 0.02. Then F3 is 0, negative 5, and 0. And then R3 is equal to 0.6, 0.45, and 0. Okay, so do all of these look right? I don't see a difference. You don't actually need to write the 0. You can put 0.48 and that should be the same thing. Looks good. Okay, so let's before we look at the answer, let's predict what this should be. So we've got some Z. These ones don't really have much Z. A little bit more down than up, and a little bit to the right. So the force is generally in positive X a bit in negative Y, and a fair bit in positive Z. So that means that the reaction force should do the opposite of that. We expect the reaction force to be in a little bit in negative X, a little bit in positive Y, and a bit more in negative Z. So let's check. FA is equal to negative F1 plus F2 plus F3. And yeah, I think that's what we said, right? Negative X, positive Y, and a bit more in negative z. Yeah, good. So then MA would be equal to negative because we'll bring these terms over to the other side of the equation. MA is equal to negative R1 cross F1 plus R2 cross F2 plus R3 cross F3. Let's see how that goes. I'm not going to look at this. I'm going to think about this problem first so we don't lose the opportunity to do a check here. Let's see. So the forces here were generally to the right, down, and out. So like that way. And these ones were kind of up that way, which means they're going to tend to make it spin around like this. So I'm going to need a moment that's sort of up and to the left away to cancel that out. So let's check. We've got a moment which is negative x, yeah, okay, back that way, and up, and positive z. Is that sort of up and to the right away? Yeah, I think that's good because it was, yeah, excellent, perfect. That makes sense. So this is hard. There's a lot of challenge to visualizing these things, and it's easy to mess it up. So you want to use all the tricks in your toolbox that you have, which is like visualizing it first, double checking that things make sense, predicting what the answer should be, and then calculating, and that will help, but not completely. That'll help you eliminate, but not completely eliminate errors. So the other part that will really help eliminate errors is remembering that that any one approach will not work to eliminate errors. It's always got to be like a full-on due diligence, ever vigilant process to make sure that you don't make mistakes in engineering designs. All right, next thing, we're going to be trying to find out the reaction forces and moments on B, reaction forces and moments at B, I should say. And the way we're going to do this is by finding the net force on the gray beam. On the gray beam alone, we've got the net force, and here I'll make this a little bit smaller, would be the total forces acting on it. Would be, again, 0. And we've got the force from B. It doesn't see force of A because that's not directly applied to the gray beam. So reaction force from B. We've got the reaction force from the cable, which we can call CD, from point C to D, that cable. The force 1, force 2, force 2. What I'm hitting here, in case you're wondering about math type, is plus Control B, Shift F to get those things. Anyway, Control L for the subscript, force 3. And this will be the total force on that beam. Okay, great. Where we can write out what FB is. FB is some unknown force, some reaction force, that definitely has no y component. So it's Fx, FBx, 0, and FBz. Yeah. Now we also have the cable force, FCD. What we do know is that it has to be a positive tension, and that it's going to be pointing, at least on this beam, in the direction from C to D. So we can multiply that by R hat CD, where R hat CD is defined as R CD over the magnitude of R CD, and R CD is itself defined as the vector that points from position C to position D. So that'd be final position vector, position D, minus position C. Okay, so there we go. That's the 3. So we'd have 3 unknowns in the force equation. The torque equation would involve more unknowns because we have an unknown moment with 3 components applied at B. So the net torque we're still under the heading of on the gray beam alone, net torque. So we can find it about any point that's convenient. It's still convenient to find this at the origin because then we don't have to subtract vectors in the moment arms. If we found it about point B, we'd need to do something like R1 F1 minus RB cross F1. But if we just do it about the origin, we're subtracting 0, so that goes away. Okay, so this is net torque at the origin on the gray beam would be equal to the moment applied at B, the moment that this reaction, this joint is applying to the gray beam, because it can apply a moment, plus RB cross the force that this joint is applying to the gray beam at B, plus force CD times its moment arm. So that would be RC, the distance that we are away from the origin, crossed with that force, plus F1 crossed with its moment arm, plus F2 crossed with its moment arm. And I should really be saying these backwards. The moment arm for F2 crossed with F2. Because order and cross product matters, remember. If you take the F2 and cross it with R2 instead of R2 cross F2, you'll get negative the vector that you're looking for. And finally, R3 cross F3. So let's just double check. We've got all the forces that are acting on the gray beam. And we've got the moment, the pure moment applied to it by this, this support. Okay, so there we go. And the thing we didn't define is that moment, where MB is equal to, this support can resist any rotations as we talked about before. So this is MBX, MBY, MBZ. All right, so that means that we're going to have three new unknowns from the torque equation. And with the unknowns that we already had from the force equation, we're still going to be able to solve for everything. Okay, so let's give that a shot. We can do this in a couple of stages. First, let's put in the new coordinates that we didn't need to put in before. RB is 0, 0.5, and 0. RC is 1.25, 0.55, and 0. And RD is 0.05, 1.3, and 0. Okay, so then the force equation. Oh, let's first put in the variables. Yeah. FB is equal to FBX, 0, FBZ. How about working out RCD hat? Maybe just work out RCD first. RCD is, whoops, at the automatic Windows key that makes us hit emojis. Right, we don't need that. RCD is equal to RD minus RC. And then we've got the FCD, which is given by T times RCD divided by the norm of RCD2. So the 2 norm, which is the magnitude. Let's just double check that that looks correct. Yeah, okay, so we got one vector there, and it goes left and up. Okay, good. Yeah, so then the next thing is the force equation on the gray beam, which would be FB plus FCD plus F1 plus F2 plus F3. So that's our force equations, and we should have that this is all equal to 0. And you can see that this would be enough for us to solve for those 3 variables. Next, we've got the torque equation. Torque, maybe I'll use a capital G. Bit of a camel case there. Torque gray equation. Camel case, so-called in programming because it looks like it's got like humps for the capital letters, small letters, and then a bump when you have the capital letters to show off the different words. Yeah. Okay, so torque gray equation, and we've got this one. Right, so we need actually first to define MB, MBX, MBY, MBZ, and then we'll have torque equation is MB plus RB cross FB. I think you need the space here, otherwise it's going to interpret it as a single variable, but you don't need the space in front because you're not allowed to have an ampersand in your variable name. So this should work. It's, I mean, it's the wrong equation, but I'm pretty sure that you can avoid the space there and leave 1 there. Right. Okay. RC cross FCD, R1 cross F1, R2 cross F2, and R3 cross F3. All right. So this one, as promised, has extra unknowns. We've got FBZ showing up in there. We've got FBX showing up in there. Just as a check, FBZ seems like it's making torques in the X direction, potentially. So more force on B in the Z direction would be making torques about X. Does that make sense? Which way is this displaced? Was that negative or positive? 0.5. Positive 0.5 in front. So that means that a force on this in the positive Z direction would mean, which is out of the page, displaced to the right, would mean a torque showing up on bar B about the origin in the X direction. Does that make sense? Okay, so the torque in the X direction is to the right, which would mean spinning kind of out of the page and toppling forward. Yeah, okay, so we're not displaced to the right a little bit. We're just purely vertically up, and if we pull that out, then that'll make this topple forward, which would be a positive X torque. So here's this diagram in 3D with a bunch of other things drawn on it. Don't worry about that. For now, this is finding the torque from F1 from the lecture notes. What I mean by topple forward is a force pulling out in Z at B will make this thing spin about this point, right? It'll get spin this way. That would be a positive torque in X, right? And if you curl your fingers in this direction and point then your thumb can point in the positive X direction, which is over to the right. Yeah. What about the other one? So this last force, the place that the force shows up in the last term here, in the Z torque, is with negative. So it's saying FBX decreases the Z torque, or in other words, by itself, an increased FBX, which is the force to the right that this is putting on this thing, would tend to spin us the other way about Z. What is this spinning about Z? Spinning about Z is, well, Z is out of the page, so a positive torque in Z would be that way. Aha, well, force this way on the beam to the right will make it spin the other way. It'll make it go like this in Z, and that's negative Z spinning. So negative Z torque is what causes it. So after a few checks, the equations seem good. Now we're in a position to solve them. Solve. We're going to put in brackets here. Actually, it's good to double check that the equations that we're giving to solve work out. I don't want to do this in too many steps at once. So let's go sequence F gray equation n. N is 1 to 3. Then we'll comma that with torque equation, torque gray equation, n, also a sequence of this, sequence torque gray equation, n is 1 to 3. Okay, let's see. So this should be all of those equations, each separated by a comma. And if we use the percent symbol now, do we get all of that back? Yes. Repeats everything that was evaluated by this last full command. So not just this first term, but the second term as well. So if we take this thing and we put it in square brackets, now it's something we can pass into the solve command and should be able to uniquely determine an answer for all of those variables. If it turns out the system was not statically determinate, then you might get a problem at this step. The issue is, with round-off error, it's possible that you have a redundant equation. It's actually statically underdeterminate, but you have one of the equations twice, and then it'll give you a solution because it thinks you have extra information. Actually statically indeterminate. It's actually statically indeterminate, but it'll give you a solution from thinking you have extra information from the round-off that shows up from one equation to the next. So be careful. Some strange things can happen if you have the same equation put in twice. This will usually only happen if you try and do funny things with the torque equations. So you take the torque about one point and then you take the torque about another point that ends up giving you some redundant information with the first one. If you just stick to using one torque equation and one vector torque equation, like we did here, and one vector force equation, then this issue won't come up for you and you'll be in good shape. So you'll have an error show up here, like no solution. If it turns out there actually was no solution, it was underdeterminate, and you'll just have parameters left over if it was indeterminate. Let's do that. We can make it indeterminate right away by imagining that instead of a slider, it was a fixed support here, right? So if we put FBY, now we have too many constraints. It's not that there's no solution, it's that there's infinite solutions. So now what we have is a parameter left over in the end. Maple has said, let's let FBY just be FBY, and then everything else we can answer in terms of that where necessary. Yeah? But that doesn't show up if you have exactly the right number of supports. Everything's solved uniquely. What about underdeterminate? Can we explore that? Well, yeah, that'll be if we put in something else is 0. So let's see this. Suppose this can't apply force in X, actually, right? It's like a two-dimensional slider. Then you can tell from a physics perspective this isn't going to work. When we try and pull on this cord, when we give this some tension to hold this up, then we need to counteract it by pushing to the right. So if we set this to 0, there should be no solution. Let's see what Maple does when we have an underdeterminate system. Okay. So solve output this, right? No. This was the output from the thing before the solve command, the sequence thing we were looking at. Solve output nothing. So this is telling us there's no solution. Sometimes it'll throw an error. Sometimes it'll tell you that it can't solve it. Maybe it'll answer in terms of the question you put in. I guess that's like, yeah. Not like on Jeopardy. It'll just give you the question back in the exact same form you asked it. But in this situation, it output just nothing. So you've got to look carefully at your output to detect whether or not something has gone wrong and it got rid of the solution that it was giving you before. Okay, let's have a look at it then. We've got FBZ is negative 3.6. Since this is the only thing providing the Z force, and the Z force we're applying is the same at B as it was when we were on the full structure, we expect that this is going to be the same Z force as A needed to provide. Yeah, because the cable's totally in XY, we're not going to have any modification to what needs to happen in Z at this support compared to what we did there. What else? MBX, small, not a very big moment compared to some of the other ones. The moment on B in the X direction, that's this one, this twisting moment. Well, these forces are not very far away from the line of action of B, so they're not producing a lot of torques that we need to cancel by applying a direct moment there. Everything is at a pretty small perpendicular displacement away from this X-axis parallel line coming off of B. What about MBY? The MBY is the moment pointing up this way. That'd be spinning. Let's get the 3D thing back. The moment pointing up there is for spinning like this, right? About that y-axis, which is the up and down one. Okay, so we have what? We have a positive and kind of large MBY needing to be applied. Why? Why would that be? Well, because we've got a decent torque from this F1 applied there, and we need to cancel it, and we're not getting any canceling of that with the cable or with any of these forces because they're at that same moment arm spot. So yeah, we're canceling the torque provided by F1's Z component by using an MBY there. What's next? We've got tension. Tension is pretty high because this has to counteract the Z force because we can't counteract it there, and we can't counter it directly. So you expect this to be larger than the net Z force from those ones together. I think we worked out that the net Z force that we're providing is a little bit more than 2. We can look at FA to check. Sorry, I'm calling this Z. This is the Y force. Tension is correcting the Y force. Y is up. So FA needs to provide a 2.4, and for the cable to provide 2.4 up, when it's not really directed up, it's directed more to the left, it has to have a higher force than that so that its vertical, its Y component is 2.4. All right, so next, because we're pulling over to the left with this, and that's creating, let's see, FA was going to have to pull to the left, or maybe push to the left to counteract this like kind of rightward force that we're getting from F2. But now the cable is pulling to the left itself, so maybe that kind of cancels this, and probably the X component of this one is sort of small. Yeah, it is smaller. It's kind of the combination of the X component we would have needed to cancel those forces, which is in FA, and the extra amount that we're getting from adding this tension's X component. Right. So then what's next? MBZ. What's this one? So MBZ is the moment that's counteracting this rotation about the Z-axis, like that. So MBZ would make it spin more like that. What do we have? We've got again, the tension from the cable is very far out, and it's doing the Y force, and it's counteracting these things, but it's farther out, so it probably makes more moment up than the moment created by the forces it was canceling. So likely, we need to have a negative moment in the Z direction to counteract the net effect of the force reactions on here. Let's see. Yes. Okay, got it. The system works. Everything makes sense, and we solved for those reactions. All right, so that's the forces on the gray bar. We could also do a little bit of a final check and figure out what the forces are on ABD. And if we've done our equation set up correctly, then we should have net force on this is also equal to 0. So let's assign the thing that we solved there. And let's try to now take, maybe we'll go on the next, we'll run this again. Yeah, let's just go here. So we can figure out the net force on ABD by itself. So this does not see those F1, F2, and F3. And we can go FABD is equal to FA minus FB, because FB was the force that ABD is putting on this. So minus FB would be the Newton's third law action-reaction pair. And then minus FCD. Same idea for the tension. This FCD was the force that this is pulling on the gray beam with. So negative FCD would be the force that the gray beam is pulling on the golden beam with. Okay, so we should get 0. Let's check. Aha, looks good. No net force on ABD. So far, so good. How about the torque? Tau ABD will be equal to, let's find it about the origin again, moment at A. Now we've got the moment at B was same idea, Newton's third law action-reaction pair. We're going to have to subtract moment at B because what we called moment at B was the moment that ABD is putting on the gray beam. So negative MB is what the gray beam must be putting on the golden beam. And now we've got the force ones. So we've got no moment from force at A because it's not displaced at all. But we do have minus RB crossed with FB, or you could just, if you want to see that, you could say plus RB crossed with negative FB. Yeah. plus RD crossed with negative FCD. Okay, so this, if we haven't forgotten anything, should be the net torque on ABD. Do we get 0? Yes. All right, lots of checks, everything looking good. This also illustrates a different way that we could have solved for this reaction force at B and this cable force. A different way that we could have done it would be to do the net force on ABD instead. So that's after we've got the first part. Go back to this part of the problem. We now are in a position to just start off everything, not with these equations for the gray beam, but with the force and torque equations for ABD. Whoops. We need to define what ABD, what FB and MB are again. Okay, so still put in the definition of what FB is. We've kept it the same sign, so it's still the force that is applied by ABD, and same thing with our CD and FCD. So these and the moment. So these are actually negative, the ones that are applied on ABD, but we could have reversed the sign if we wanted. We'll just have a different definition of them, and then we'd get negative the values we got earlier if we do that. Okay, anyway. Now we've got these equations set up, and these are also 6 equations and 6 unknowns. Now that the force on A is known, because we figured out the force on A and the moment on A, even though this would normally involve kind of 6 unknowns from there, and then 5 unknowns and another unknown, it would have had 12 unknowns and only 6 equations. By doing the whole equilibrium of the entire structure, we've already sorted out how that, we've already sorted out what 6 of the values are, the values for the forces and moment components of the reaction at A. So now we're in a position to again say, solve sequence FABD n equals 1 to 3, and sequence tau ABD n equals 1 to 3, and yeah, solve that, and we should be able to get all of the same values as before. Okay, same tension, same moment about the y axis applied from ABD to the gray beam. Yeah, exactly the same. So whether you find out what the reaction forces and moments are on the gray beam by looking directly at it, or you look at ABD once you've looked at the whole structure to find out the reaction forces and moments at A, up to you. Either way it should work out. Lots of good checks that we can do in this setup, and everything seems consistent. Thanks for watching. I'll see you next time.